Hello, everyone, and welcome to another Open Rewrite Community Office Hours. I'm your host, Sam, VP of Engineering at Modern. Unfortunately, Tim will not be joining us today as he's off doing exciting things. I forget exactly why he's not here today, but it's usually because he's presenting at a conference or traveling somewhere so that he can present to a conference. So let's just jump right in with our announcements. So to start with, the latest version of the Modern Monthly newsletter published on LinkedIn is available. A lot of good stuff in here. Uh, in terms of podcasts that we have been on, that Jonathan has been on, upcoming talks, past talks, a video where you can meet Tim, very popular one. If you're a regular viewer of our office hours, you've already met Tim. Uh, but for anyone else, he's a good guy to get to know. Plus a selection of our other content and relevant presentations. So if you're not already subscribed to that, consider doing so. In news of upcoming events, in 15 short days from now, I will be doing a free webinar through No Fluff, Just Stuff on migration engineering with OpenRewrite. And we're going to talk about recipe authoring and recipe execution, and well, many of the same sorts of fun topics that we talk about on these community office hours. So if you've been looking to improve your recipe authoring skills or get more foundational knowledge about how OpenRewrite or Modern work, I encourage you to join me then. And then at Spring I/O, Tim is actually going to have two sessions coming up. So if you're thinking about attending Spring I/O, be sure you check out Tim at his automated software refactoring with OpenRewrite and generative AI presentation, as well as the fundamentals of migration engineering with OpenRewrite, which will be an interactive workshop. I believe this will cover pretty similar material to what I will be presenting at that No Fluff Just Stuff workshop. So if you were planning to attend both, you could probably do one or the other, or you could or you could attend both, and then decide who does a better job of presenting the material, Tim or I. We should put up a poll or something where people could vote about who the best teacher of Open Rewrite is. So let's see. I think that is all of the announcements we have for today, and the topic I was going to cover uh, in this session was kind of how some of our parsers work, right? We talk a lot about recipe authoring and the thing you can do with Open Rewrite, but if you want to get under the hood, if you want to expand the capabilities that Open Rewrite is capable of addressing, well, it all kind of begins with a parser, and I think we'll probably actually start with the Java parser. Let's see. Is this, you know, zoom in my text size a little bit here, try to keep this a bit more legible. So fundamentally, the way or I kind of think of it as there being kind of two kinds of parsers in Open Rewrite. There's the parsers that we build around an existing language compiler, and there are the parsers that we build around an ANTLR grammar. And we'll kind of talk about both of those here. I think we'll start with the Java parser, as most people are coming to Open Rewrite to manipulate code and incidentally data. So we'll start with how code works and then talk about how data files work. So for the Java parser specifically, it's kind of interesting in that since we're running on a JVM, uh, the and we need to access Java compiler internals, or rather, how the Java parser works is that we will invoke the actual Java compiler, and we will tell it to, Lex, tokenize, parse into an abstract syntax tree, type attribute that abstract syntax tree, and then we take the Java compiler internal representation of the code and map that onto the Open Rewrite representation of code that we call the LST, the lossless semantic tree. Um, bit of fun trivia. We originally just called the data structure that recipes operate on an AST, an abstract syntax tree, the same term compilers use. Uh, but part of why an abstract syntax tree is abstract is that it throws away information from the source code, right? It throws away comments, it throws away white space, it throws away any aspect of those source files which is not relevant to going on and generating the bytecode that's actually going to be executed. But since the purpose of OpenRewrite is ultimately about manipulating or extracting information from source code, not generating bytecode, we do care about all that stuff. So we were keeping all of the information that that an abstract syntax tree normally wouldn't include. And someone, I don't know who it was, but someone kind of snarkily said to us, "Well, it's not very abstract anymore, then, is it?" And we were like, "Well, good point. We should use a different term." And so we could have gone with like concrete syntax tree. CST is a term that is sometimes used to describe a tree-based structure that does not get rid of that information. But we wanted to reflect that that it was that the data structure was representing more than just more than just the syntax, that it had additional information, that there's the stuff that's in those helpful markers of there's dependency information, that there's type attribution. And so that's kind of how we ultimately got to the term lossless semantic tree. But the first step is to get for a language like Java is to get the actual Java compiler to produce its LST and then we map that onto our representation. So since we need to access Java compiler internals to do that, well, one, OpenRewrite has to be running on a JDK. Just a JRE isn't enough, which I'm sure you're all already aware of. Since a JRE doesn't contain the compiler or the compiler tools, we need to be running on something that does have those things. And then it also means that since to parse Java code, we have to use the Java compiler. Well, not have to, but the way it works right now is that it's going to use the Java compiler that's associated with the JDK that is actually running the OpenRewrite process, which could potentially lead to a bit of friction in some cases if you were like running on Java 21 but parsing Java 8 code. I think we've worked through most of those issues now. And then we do some indirection and some reflection like stuff to try to avoid having to slap on those dash dash add exports arguments that started becoming mandatory around the Java 17 timeframe. So that's why there's this what we call these reloadable parsers. So here's the implementation of the Java. So there's one kind of Java parser implementation per major JDK version we support. So there's rewrite Java 8, rewrite Java 11, rewrite Java 17, rewrite Java 21, and all of these are set up so that they can coexist on the same class path at the same time. And you can use Java parser dot from use Java parser dot where to go? Oh, it's right over here. And then we have Java parser from Java version is going to go look up the appropriate parser class to use based upon what version of Java you are currently running. And of course, the appropriate implementation of Java parser has to be on the runtime class path of your of whatever process is going to be parsing this code. But let's say you're running on a JDK 17 and it has selected the Java 17 parser. This is where we kind of get into actually beginning the parsing process. And so if you have ever wanted to use the Java compiler like a library yourself, here's some good examples of kind of how you could go about that, where based upon the configuration that's passed into the parser, we configure the relevant objects for the JDK's Java compiler, and then tell it to kind of go do its thing. And so once the compiler is configured and it's time to pass in some source files to it, it's going to come down to this parse inputs function, which you see here. It's newing up the Java parser, and then it uses this parser.scan method, uh, and we provide. This guy actually going to have. Let's see, parser visitor. Yeah. So yeah, this parse inputs method is going to use this what we call the reloadable Java 17 parser visitor in order to translate the Java 17 compiler's abstract syntax tree into the OpenRewrite LST. So the kind of the meat or the main contents of parsing are going to or the main the heart of translating the Java compiler LST into the Java compiler AST into the Open Rewrite LST actually happens inside of this parser visitor. And you'll see for most of our parsers that there's a class inside it somewhere called the parser visitor. And that's always the job of that class is to translate the compiler or the ANTLR or whatever parser we're kind of building the Open Rewrite parser around's representation into the LST representation. And so the parser visitor here, if you were to look through its methods, you would see a lot of methods that look pretty similar to what you're maybe already familiar with from writing a Java visitor. You'll see methods for visiting annotations. You'll see methods for visiting class visiting oh, yeah visiting class declarations, although the names are a little bit different than what you might be familiar with, because this is the Java compiler internal visitor class for visit that it uses at various stages throughout the compilation process, for generating bytecode and the like. uh, and what we use so the Java compiler calls its visitor a tree path scanner, and we're making a tree path scanner that produces a J that produces an LST. And so kind of what we do is we have mapped fairly directly, in the case of the Java compiler, um, the AST elements to LST elements. So if you ever saw something in the Open Rewrite Java LST and you're like, that's weird, why is it organized that way? Chances are it's organized that way because that's what the Java AST was like. And so, so for like we're gonna like visit a compilation unit, which is the highest level of AST element as well as the highest level of LST element for a Java source file. And in here, you kind of do the translation. You have some object that's coming in from the Java compiler itself, and ultimately we're going to be returning the J, the LST element that your recipes are going to operate on. And but the challenge is, or one of the challenges involved in this process is that the Java compiler LST doesn't, like I said, already doesn't contain white space or comments, and we need to include all of that information in the Open Rewrite LST, or we won't be able to faithfully reproduce the source file that you are parsing, and won't be able to change it or produce working patches or diffs. So a good deal of the logic inside of here is is white space handling, or dealing with the tokens. So you'll see commonly functions like this source before function is like white space handling, essentially, where we're saying until some delimiter appears, put all of the white space and all of the comments you encounter into one of these space objects, which in the case of Java represents, 0 or more comments along with some white space. Most recipes don't have to think about that very much unless you are writing a recipe that is explicitly about manipulating formatting or white space. So, yeah, a lot of what goes on in these parsers is taking the Java compiler AST and just like the raw textual representation of the source file and kind of traversing through both in parallel or in tandem at the same time to match up the white space from the raw source file to the structured hierarchical objects that the Java compiler LST gives us, so that we can produce the LST, which has both of these things married together. And kind of the way that we keep track as we go is, inside of the parser visitor, you'll see this innocuous little integer field called cursor, which is used all over the place. 59 usages all within this file, and this is just keeping track of where in the string of the source file you are currently reading from. So as we kind of advance through the structured representation, as we advance through the LST, we increment this cursor to match so that we can always kind of associate the structured object with a particular place in the stream of text so that we know where to grab that object's white space from and stuff it into the LST. Let's see. And then there is kind of for Java and other programming languages that have a concept of types. The type attribution for the symbols you're working on is incredibly important to these symbols working correctly. And we have OpenRewrite has its own implementation or its own representation of Java types under the very creatively named Java type class. So there needs to be some also for type metadata. There needs to be something that translates the Java compiler internal representation of a type into the OpenRewrite representation of a type, and that is the type mapping, which takes in a Java compiler internal representation of a type and returns the OpenRewrite representation of a type. So if you ever find a bug in type attribution in OpenRewrite that isn't there in Java, it's probably a bug in here somewhere. And this guy has to do a decent amount of some caching and deduplication type stuff, so as to avoid having multiple different objects representing the same information. If you ever were to look to fix a bug in here or make some change to how type attribution works, there is we have created this kind of interesting and anachronistic file, like Java source file that we call the type goat. And this is pretty much a nonsense source file, or rather, it's syntactically valid, but the purpose of it is to kind of try to represent its test collateral. Essentially, we make a test case out of this where we try to represent every kind of like weird type situation with that there can be in Java. Every strange type parameter combination, features that you may not have even seen, like using this and symbol when creating generics, mess with inheritance, mess with annotations, enums, just kind of every situation we could find or think of that results in a unique representation of a type within Java. And so we have some tests that parse this file and then check that everything gets represented correctly in the OpenRewrite type system. So just to kind of summarize what we've talked about so far, the Java parser class or the Java parser interfaces from Java version method will select an appropriate parser implementation based upon what JDK you're running on. That reloadable, assuming the example of Java 17 hereafter, the reloadable Java 17 parser or the Java 17 parser will do reflection-y things in order to construct a reloadable Java 17 parser in such a way that you don't have to do a lot of adding dash dash add export JVM arguments to any process that you want to use an OpenRewrite parser within. Uh, that kicks off the reloadable Java 17 parser, which is going to use the Java compiler internals visitor pattern, which it calls a scanner, with the reloadable Java 17 parser visitor in order to map the Java compiler internal representation plus the white space coming from the raw text of the source file together into the Java LST, and it will be using the reloadable Java 17 type mapping in order to translate the Java compiler internal representation of a type into the open rewrite representation of a type. And once all of that is done, you have your LST and you are ready to go. Yeah. So, feel free to ask any questions about this stuff in chat. But that's more or less how like the Java how the Java parser works. And once you kind of understand that, you're probably ready to uh, dig into and fix bugs inside of the Java parsers. But these guys are pretty stable, so we don't have bugs in here too terribly often. Yeah. So let's see. So that's how a parser that is based on the compiler for an existing language kinds of works. But sometimes we're not basing a parser on some existing compiler. We are for like a data format. Well, I guess I would say even for Java, if we didn't want type attribution, like if that just wasn't important to us or it was easy to get by some other means, we would probably just make a parser out of an ANTLR grammar. ANTLR being a versatile system for generating parsers from context-free grammars. We would probably, rather than dealing with the complexity of using the Java compiler, would use just a parser generated from the grammar, except that doing your own type attribution is fiendishly difficult, right? It's doing type attribution is than doing um, harder than any other part of parsing. So it's possibly fair to say that the reason we do use the Java compiler rather than making our own parser out from an ANTLR or from a context-free grammar is just so that we don't have to do the type attribution ourselves. Because it's the type mapping is a lot easier. The Java compiler goes and does the type attribution, and then all we have to do is take the finished result and map it onto our representation. That's a heck of a lot easier than actually doing the type attribution yourself, which is only getting harder and more complicated in modern languages that have lots of powerful type inference and allow the and have complex and powerful type systems with not just inheritance and various forms of polymorphism, but intersection types and union types and all of these other kind of higher level constructs of type information. So that's something that's getting more difficult in modern programming languages to do. So for those, we will probably continue as much as possible to lean on an existing compiler implementation. But for data formats where there is no type attribution or there is no meaningful type attribution, an ANTLR grammar is going to work great. So for something like JSON, we don't need to go to someone else's parser representation. We can just make an ANTLR grammar or take an ANTLR grammar that someone else produced. Uh, as noted in this in this comment, so inside of rewrite JSON, if you look inside of the ANTLR folder, you will see the files that define the structure of a JSON document. If you may or may not already be familiar with a context-free grammar, but if you let's JSON path parser, that's not relevant. But if you're familiar with like writing an open rewrite visitor, some of this stuff is probably already, kind of makes sense to you, even if you don't know too much about context-free grammars, because you'll have you'll have like a root level element like a JSON5, and a JSON5 is made out of a value, which, just like in a regular expression, the question mark kind of denotes optionality, and the end of file terminal symbol. Um, so, an empty string, according to this, is a valid JSON5. And one thing that's really handy if you're ever working on these is to have the IntelliJ ANTLR plugin involved, and so that you can open up one of these G4 files and not only have syntax highlighting, but click test rule. And one of this kind of little window will pop up for you and allow you to put in some text on this side. And assuming that it's valid according to the grammar you're providing, it will show you the abstract or the syntax tree that is parsed into, or I suppose it calls it a parse tree. So, as we see, just the string ASDF is a valid JSON5 document, which it interprets as, JSON5 is made out of a value, or a value and an EOF. And in this case, that value is a string with the literal value ASDF. And if I, put some other stuff here that isn't valid, it highlights immediately how it is not matching the expectation of the grammar. Yeah, and so in here it's like, well, you can't do a pairing without, a value can be a number, an object, an array, or a literal, but a pair is not one of those things. So but if I go find the definition for object, where did the definition for obj go? Yeah, so we see here the definition for an obj, or an object. It begins with a colon, then it has some members, and then, or not a colon, it doesn't begin with a colon. It begins with a curly brace and is ultimately closed by a curly brace. So this tells me that I could probably make a valid JSON document by putting some curly braces around this. And so we see now that this JSON5 document is made out of, a value, which is an object or an obj, and that obj has a member, and that member is made out of a key value pair, and both the key and the value in this case are string literals. So if you're familiar with writing a visitor, this is probably already kind of making sense to you, because there's a fairly direct mapping of these to, much like you saw how the Java compiler internal representation maps fairly directly to the OpenRewrite representation. There tends to be a fairly direct mapping of these objects to the OpenRewrite representation. So from this context-free grammar file, there is a build step that we only actually run if we update the grammar, this generate ANTLR sources task in the build.gradle, which will run if we make changes, that will go and populate the stuff under this like org OpenRewrite JSON internal grammar, and you get a parser generated by ANTLR representing the grammar we have just done, or we have just seen and been exploring. And if you look in here, this is all fairly dense generated code that you wouldn't want to edit it by hand because it's generated, but it's just like ANTLR saves a lot of time in generating a basic parser, and indeed it generates with it a a visitor pattern, right? And then much like we do with the Java compiler internal visitor pattern, we similarly will have a JSON parser visitor, which uh, extends the generated the ANTLR generated parser visitor pattern in order to map the ANTLR generated parser representation onto the OpenRewrite representation. And then kind of just like you saw in the Java parser, and we'll see in most of our parsers, there will be a cursor that is then used to keep the traversal of the structured representation, the AST, aligned with the our place in this string representing the source file, such that we can again kind of combine all the white space and comments, because ANTLR generated parsers don't care about white space any more than the Java compiler internal parser. So that's kind of why we can't just stop with the ANTLR generated parser. We still have to do a bit more translation on top of that, so that we can grab all of the white space and stick it into the our LST representation. So yeah, let's see. I think that has kind of covered the basics of how parsing typically works in OpenRewrite. Now, typical is one thing. There tends to be some variation in every single parser is a little bit different, right? Like in Maven land, it's a Maven POM is an XML document. So what the Maven parser does is mostly layer dependency information on top of an existing XML document. The Groovy parser, well, Groovy is a very similar language to Java in many ways. Its parser and its compiler look very different for reasons that I'm, still not sure of. Even though I spent a lot of time working in the Groovy compiler, they internally, like the Groovy compiler itself, internally has not one visitor pattern but two. So there's both a what they call a Groovy class visitor and a just a regular visitor, and we have to implement both and go back and forth from one to the other in order to successfully parse Groovy. And the Kotlin compiler is a whole other can of worms, but these kind of basic patterns I've talked about mostly hold true, but there's always some idiosyncrasies involved in adapting to the specific grammar or the specific compiler that you're working with in order to produce the LSTs. Um, so some of the complexity here might be why, if you're wondering why we don't support your favorite language yet, well, some of these complexities might be why. But yeah, we are working on C# right now. Canute is busy with that, and I'm sure we'll have him on the office hours to talk about how that works once he is a bit further along with it, or once we have a first kind of version of C# support to show the world. That one actually has some really interesting stuff going on, because you know so far all the parsers I've shown you are things we can run on the JVM, but obviously, the C# parser doesn't run on the JVM. It runs on the common language runtime that all .NET processes run on. But we don't want to have to replicate all of the recipe execution infrastructure in .NET in order to be able to work with to produce and work with LSTs for C# code. So Canute has come with some really clever ways of remoting, of serializing information back and forth between a JVM and a CLR process, so that we can will support recipes written in C# and recipes written in Java, kind of or written in JVM languages, kind of regardless. So look forward, if you're interested in how the parsing works and how the LSTs come into existence. Look forward to the C# implementation, and for Canute to talk a bit about that, because there's some really interesting stuff there. So yeah, I think this has been kind of a little bit of a crash course in the basics of how the parsers work. I hope that this helps you to uh, appreciate why maybe the LSTs are the way they are, and maybe even if you were feeling ambitious, start to have an idea of how you might go about adding support for your favorite language or data file format to OpenRewrite. Uh, Although if you were thinking about writing a parser for OpenRewrite, that's something you should get in contact with us about. Talk to me about it on the open source community Slack. I'd love to support you in that project, but it is difficult, particularly if you haven't written parsers before. You might struggle with it, or you might produce a parser. Yeah, just come talk to us, and we could help steer you down the right path and away from some frustrating dead ends. Uh, So yeah, I think that is probably a pretty good place to end it. Thank you for coming. Hopefully you found this exploration of the open rewrite parsers to be useful and interesting. And I hope you have a great week, and I'll see you again next week. Bye for now.